basically what I'm doing is I'm retrieving DNA, genetic information of animals and plants directly from ancient sediments. And this DNA comes from feces, from leaves, from roots that is being degraded, so you can't see those anymore, but the DNA is still there, so you can tell what kind of animals and plants were in fact living tens of thousands of years ago, hundreds of thousands even. We really don't know precisely how it's getting into the ground, but we think it's actually coming from roots and stems from leaves from the vegetation, right? And for the animals from feces and urine, and that's kind of mixed into the sediments, and the cells are being degraded, etc. So you can't see anymore that it was feces or leaves, etc. But the DNA is still preserved there in the sediments. There's a big difference between the past and now. I mean, if you just go back 10, 12,000 years ago, I mean, there was mammals around in the northern hemisphere like woolly mammoth, woolly rhinoceros, right, steppe bison that you just don't see today. They're gone extinct. So you can say the whole fauna, but also the vegetation was very different from now at that time. What is really interesting about the bacterial DNA is that it seems like some of that can actually be reused by living bacteria. So it's getting into the genome, the genetic makeup of living bacteria. So that means they can actually obtain genetic signatures of the past. And what is the consequence of that, we don't know. And we don't know how often it happens, but we do know it happens. I believe from our data that climate change has been a major driver of extinctions and changes in the environment. And, you can say, given what we are experiencing today in terms of climate change, I would expect that we can see really massive changes in our surroundings. I mean, we are talking about climate change, 10, 12,000 years ago, caused the extinctions of 2/3 of all the mammals on the northern hemisphere, right? I mean, it's a pretty significant impact.